Chapter 9, Work and Energy. 9.1 Introduction. On May 18, 1980, an explosion shattered the countryside in southwestern Washington. Mount St. Helens erupted for the first time in more than 100 years, hurling nearly 27 kilometers of solid rock and ice 4 kilometers into the air. The volcano devastated more than 500 square kilometers of the surrounding land. To cause the same amount of destruction using nuclear bombs, one Hiroshima-sized bomb would have to be set off every second for 7.5 hours. The neighborhood of the volcano was changed from a life-filled region to a wasteland. This explosion is an example of the unrestrained release of energy. Even explosions, however, can be contained and made to do useful work. A gasoline automobile engine, for example, is powered by explosions. Gas and air flow into a cylinder where a piston compresses them into a small volume. When a spark ignites the gas, the mixture explodes, pushing the piston away from the spark plug. This push is the source of the force that turns the wheels of the car. Both explosions illustrate one attribute of energy. Energy has the ability to do work. That is, energy can move matter. The work may be useful, as in an engine, or destructive, as in a volcano. Eruption. This chapter will discuss the relationship between work and energy. 9a. Work. 9.2. Defining work. The word work can mean many different things. It can mean exceptionally hard labor, an artistic achievement, a job, or any physical or mental effort. In physics, change the state of a system. U. However, it means the energy required to move, or can easily understand that it takes more energy to move a more massive object than it takes to move a less massive one. For example, you must use more energy to carry a 101 kilogram box 10 meters than to carry a 5 kilogram box the same distance. Also, you use more energy to move the same object a longer distance. It takes more energy to move a box 10 meters than to move the same box 5 meters. Considering these facts, it is not surprising that work, W, is defined as the product of the force component that is parallel to an object's motion and the distance that the object is moved. Mechanical work is done by a force on a system. It is important to identify the force for which work is to be calculated and to identify the system on which it acts. In symbols, W equals F d cos theta, 9.1, where W is the work done by a force F through a displacement d. It is not necessary for the force causing the work to be parallel to the displacement. The angle theta is the smallest angle, less than or equal to 180, between the force and displacement vectors when they are placed tail to tail. Notice that work itself is a scalar and can be positive, negative, or zero. Work is the scalar product of the magnitude of the displacement, distance d, and the magnitude of the force component that is parallel to the displacement, F cosine theta. The angle between the force on a system and the system's displacement determines the quality of work done. If 0 is less than 90, equation 9.1 is positive. Therefore, positive work is done because the cosine of angles less than 90 degrees is positive. If 90 degrees is less than theta is less than 180 degrees, the cosine of the angle is negative, and work is negative. Negative work by the force occurs when the force acting on the system opposes the motion of the system. If the angle between the force and displacement is 90 degrees, they are perpendicular. There is 0 work done by the force on the system, because cosine 90 degrees equals 0. 9.3 Units of work. The units of work can be found from equation 9.1. In the SI, F is measured in newtons, and D is measured in meters. W equals newtons times meters equals N.m. The SI unit of work and energy, the Newton meter, has been given a special derived unit name, the joule, J. 1 J equals 1 N times 1 meter. The joule is utilized for all forms of energy and work. For mechanical work, the units Newton meters may be used. Be sure you do not confuse this unit with the unit of torque, also the Newton meter. Torque, unlike work and energy, is never expressed in joules. 9.4 Calculating work. Any kind of force can do work. Contact forces as well as action at a distance forces move objects and therefore do work. For example, a weightlifter exerts a contact force on a barbell that he does work on by lifting it, and the Earth exerts the force of gravity on a falling rock that it does work on by pulling it down. Although any kind of force may do work, not every force on an object will do work. For example, suppose a rock is at rest on a table. The Earth exerts a gravitational force on the rock, but the rock does not move. How much work has the Earth done on the rock? Baksham FG x 0 meters. OJ. The Earth does no work on the rock. Now suppose that the rock is pulled along the horizontal table by a string tied to it. The rock moves a distance of d. Now what is the work that the Earth does on the rock? Wg equals Fgx d equals negative Fw d cosine theta. Wg non Fgd cos 90 degrees. B. Der Fgd x 0. 0j. The Earth still does no work on the rock because the component of the force of gravity on the rock in the direction of the rock's motion is 0. The tension in the string, however, does positive work on the rock. 9.5 Determining work. Graphically, constant forces. Advanced methods of analysis often use graphs to show how two related variables determine a third. You have seen in previous chapters how the area under a curve approximates a quantity, finding displacement from the area under a velocity time graph. Similarly, it is sometimes useful to plot the force doing work versus the displacement. As you may suspect, the area under such a graph approximates the work done on a system by the force. We will first consider a simple case involving a constant force. The vertical axis represents the component of the force parallel to the displacement. Positive values indicate the force is in the same direction as the displacement, while negative values indicate the force is in the opposite direction. For constant forces, this graph will be a horizontal line. Figure 9-6 gives the force distance graph for the previous example. The constant force is calculated as follows. Fex seconds 30.0 n, Chaos 60.0 degrees, Charter 15.0 n. The force is the same after the mower has traveled 0 meters, 5 meters, 15 meters, and any other distance up to d equals 20 meters. The area of the shaded block is A equals the absolute value of fxd equals w. You can use the area under the force distance curve to represent the work done. This is true for any force distance curve. If you have trouble recalling the equation used to calculate work, you can use geometry to find the area under the force distance curve. Remember, the physical size of the graphical area, e.g. in square centimeters, is not important. It is the product of the dimensions represented by the horizontal and vertical axes that matters. 9.6 Determining work. Graphically, variable forces. A force distance graph is especially helpful for a varying force. For example, the external force required to stretch most springs is proportional to the displacement that the spring has been stretched. That is, Fex relate D, where Fex is the external force and D equals delta x equals x squared minus x1. The position x1 is the normal or relaxed length of the spring, called the equilibrium position. This observation is known as Hooke's law. It can be made into an equation by including a proportionality constant Fex equals kd, 9.2. The proportionality constant k is called the spring constant, which is nearly constant for real springs. In a spring system, the motion and the force are assumed to act along the same one-dimensional coordinate axis, with the origin placed at the spring's equilibrium position. Notice that as a force is applied to stretch or compress the spring, the displacement is in the same direction as the external force. So work done on a spring by an external force is always positive. As we have done with other idealized dynamics analyses, We will rely on ideal springs in discussions involving Hooke's law. Ideal springs have no mass, and the value of K for the spring is truly constant throughout its range of displacements. Many systems in nature act similarly to a spring that is displaced from an equilibrium position, particularly systems that tend to vibrate or oscillate. Any force that varies in proportion to the magnitude of displacement from an equilibrium position is called a Hooke's law force. 9.7 Work and ideal springs. How much work is done to stretch a spring from its equilibrium position by delta x? Plotting Fex versus delta x on a graph, you get figure 9-7. The shaded triangular area under the graph bounded by x1 and x2 is the work on the spring between these 2 points. The area of the shaded triangle is as follows. A equals 1/2 BH. A equals W. X equals 1/2 delta. X times K delta X. Wx equals 1/2 K delta X squared. Notice that the height of the triangle is the change in the x-coordinate times the slope of the line. In this case, the slope of the graph is the spring constant. K figure 9-7 shows the work done by a force, Fx, on the spring. What about the force that a spring exerts? From Newton's third law, you know that the spring exerts a reaction force of Fs equals negative F example. If the spring is stretched by an external force, the force that the spring exerts is Fs equals negative Kd, 9.3. Notice that the spring force is opposite to the direction of displacements from its equilibrium position caused by an external force. Therefore, the work done by a spring on a system connected to it is negative under these conditions. This equation holds true whether the spring is stretched or compressed from its equilibrium position. For example, if an ideal spring is attached to a wall on the left, as in figure 9-8, and stretched to the right from x1 equals 0 meters to x2 equals 0.1 meters, the external force on the spring must be directed to the right. The spring exerts a force toward the left, as you can see, from Fsx, Fx equals negative Kdx equals negative K times x squared minus x1. Fsx equals negative K times the difference between 0.1 meters and 0 meters equals negative 0.1 K newtons. Since Fx is less than 0, the spring force points to the left. If the spring is compressed to the left from x1 equals 0 meters to x2 equals negative 0.1 meters, the external force on the spring is toward the left. The spring, therefore, exerts a force to the right. Fx equals negative Kdex equals negative K times open parenthesis x squared minus x 1 close parenthesis. Fx equals negative K times open parenthesis negative 0.1 meters minus 0 meters. Close parenthesis equals plus 0.1 K newtons. How much work does an ideal spring do as it is stretched or compressed by an external force? Figure 9.9 gives the force distance graph for a spring that is stretched. The shaded area represents the work done by the spring force, work done by the soaring force. W's equals A equals 1/2 delta x negative K delta x. W's equals negative 1/2 K delta x square 9.4. Notice that the negative work region is below the horizontal axis of the graph. Equation 9.4 clearly shows that the work done by the spring on a system in this situation is negative. The spring force acts on the system in the direction opposite to the system's displacement. 9.8 Power. The amount of work required for a warehouse worker to carry a pallet of new coffee makers, one box at a time from the floor to a shelf 4 meters above the floor, is the same as for a forklift to raise the whole pallet at once. Neglecting the mass of the pallet, the only difference between the two instances is the amount of time needed to do the work. Up to now, you have not been concerned with how long it takes to accomplish work, only that it occurs at all. Obviously, your employer would not be happy if your work ethic followed this principle. We use machines because they help us to do work faster and with less effort. We will discuss simple machines in Chapter 10. The time rate of work done on a system by a force is called the power, P, of the force. If the total work done over an interval of time is considered, then the average power P bar is computed by P bar equals work done by F during delta T over delta T equals W over delta T 9.5. The rate at which a force does work at any instant is called the instantaneous power, or just power. Customers inquiring about power in a car engine often ask how fast the car can go. They intuitively associate power with speed. This relationship does, in fact, exist. We can expand equation 9.5 to include the work equation. P bar equals W over delta T equals FD cos theta over delta T, 9.6. But D slash at equals V bar, or just V for uniform motion. Equation 9.6 then becomes P equals FV cos theta, 9.7. Power is a scalar quantity that is proportional to the force acting on a system and the speed of the system. The unit of power is obtained from the dimensions of work per unit time, consisting of the SI units of joules per second. Because power is such a frequently encountered quantity in physics, a derived unit called the watt, W, was created in honor of James Watt, 1736 to 1819, a Scottish engineer who was prominent in the development of the first practical steam engine. 1 watt equals 1 W equals 1 joule per second.